So welcome to System Software. My name is Paul Gazzillo. I'm an associate professor of computer science here at UCF. I do research, thank you. I do research on software engineering and programming languages and security. This is a link to my webpage if you're interested in research or graduate school or anything like that. Feel free to reach out. I have lots of undergraduates who come through the lab, and if you find anything in this class interesting, we do a lot of work that's very relevant to the stuff that I'm going to show you in this class. Okay, so why are you here? I know this is a required course, but why bother studying system software? Does anyone have a reason to be here besides you have to be here? Is there something you want to learn? Yeah.
Learn about like how to like you gotta learn how to process files in the command line.
Sure, yeah. We're going to go over a lot of that. File systems, command line, some of these lost stuff that you don't necessarily get at school, and maybe you see someone next to you just blazing away at a command line. You're like, what are they doing? Yeah, go ahead.
I don't know how to use the command line. That's why I'm here.
You're going to get a crash course in about a week on how to use the command line. So good, yeah.
In order to make it, it's going to do a software engineering process. In order to make machines and build systems, is that correct?
Yeah, exactly right. So actually, you've led into my segued into my next slide, which is know your tools. This is really probably one of the more important reasons to take this class and hopefully learn something from this class. And so this is an example of Isaac Newton. Everyone knows Isaac Newton, right? The founder of sort of modern science and developed all these physical models, mathematical models. So what you might not know is that he made telescopes, he studied optics, is that he actually ground his own lenses. So this is a notebook of his where he learns how to actually grind lenses. He wasn't just sitting in an ivory tower theorizing. He actually built stuff and built tools to help him do science. So this is true of all technical workers. If you're a pilot, you go to flight school and you learn about the plane, you learn about physics. Some carpenters even build their own tools. Not everyone can go to a store and buy a tool. Somebody had to make that tool. So that's one of the important reasons to take this class. And the reason to know your tools is, if you ever heard this proverb, a poor workman blames his tools. You don't want to be that person who's stuck suffering on their machine, not knowing what to do, not knowing how to use it. And then if you're at a job or you're doing research, you're in a lab, and your work is suffering for it, no one's going to help you. You're going to lose your job. So knowing your tools well is going to help you in your job, your career, I think. And there's a more philosophical reason that I have. This quote, I thought I made this up, but I didn't, is that tools are made for man. They're made for us, humans. We're not made to serve these machines, at least in my view. So if you've ever been stuck in a machine and saying, well, why is it doing it this way? Or I wanted to program it this way, but it's not working the way I want. Oh, well, that's the machine. The machine decided for me. I want to try to get you out of that mindset that we as humans, have control over these machines. And by learning how they work, learning them under the hood, you'll have a little bit more of that control, and you won't be driven by whatever the machine or the designer of the machine decided for you. I thought I invented this quote. I didn't. This was actually Aldous Huxley and Thomas Merton. These guys actually came up with this as well. Technology is made for man, not made for technology. Little philosophy that I have. And then another illustrative quote. It's from my dad. As a kid, I would try to do something, build something, or hammer something, and he would say, don't use your hands, use a tool. And not just use a tool, but use the right tool. So don't use a screwdriver as an awl, or don't try to, because you'll break the screwdriver. So I think it's important to learn why these tools are useful, how they're designed, in order to be effective at using them, and get you out of this mindset of just thinking that if you use a certain tool, you're going to be really good at programming. So if you buy a really fast car, you're not necessarily going to be a great race car driver, right? So a professional race car driver may beat you in a slower car. And also, really importantly, is that you can actually modify your tools. These aren't just given to you from on high. These are tools written by people. And the software we're going to look at this class, the system software, is, I think, entirely open source. You could actually open up the hood, you can modify it yourself, you can build it yourself. Okay, so that kind of begs the question. Oh yeah, so my course goal here is, the kind of academic course goal, learn to use and create system software. And that's what we're gonna do in this course. And that kind of begs the question is, what is system software? This is a very fuzzy area. So if I'll give some examples of why it's fuzzy. sort of hard to define what system software is. But here I give a kind of functional definition about what it's used for. And to me, anything that's bridging the kernel, which is the lowest layer of software on your machine, and applications could be considered system software. The stuff that connects the applications that we all want to use every day on computers with the actual hardware as abstracted by the operating system. So here's a diagram of what that looks like. At the bottom, we've got the hardware. And me as a software guy, this is just given to us from electrical engineers. I don't know how it works. I don't know how to build it. I take it for granted. They've documented it. They tell us how it works. They tell how to use it. And right above the hardware is the lowest layer of software called the kernel. You probably haven't taken operating systems yet, but maybe in computer organization they talked about this a little. But the kernel you can think of it as a kind of idealized hardware. It gives you this abstract view of the hardware that makes it so that you as a software writer don't have to worry about distinctions between, say, a flash drive, an SSD drive, or a hard drive, or a network socket. The kernel just provides this kind of idealized layer of hardware. And at the top of the stack, we have the applications, everything you want to do on the internet. Look at TikTok videos or whatever you kids do these days. Write other software, do data analysis, listen to music. And it's the system software that really bridges this gap. And it's a wide, expansive, sort of ill-defined layer. In the 90s, Microsoft, yeah, go ahead.
So are system software applications like drivers?
Drivers, well, that also kind of depends. So in a monolithic kernel, that they'd be considered part of the kernel. You could consider them part of system software in a different type of kernel design. For this class, we're going to consider those part of the kernel, not part of system software. Yeah.
How about Vim? Is Vim on Linux?
I think Vim is system software, yeah. So we'll actually go over Vim in this class. So to give an example of where these definitions kind of got into legal and even kind of political territories, decades ago in the 90s, Microsoft was competing with what Netscape what Firefox used to be, Netscape, the browser. Many of you are probably too young to remember this. But Microsoft, according to rulings, used anti-competitive practices to shut out this browser. And their argument is that, well, the browser is part of the operating system. It's like system software, like a print dialog or a file explorer. And you can decide for yourself whether that argument holds water, but just to illustrate that the definition of system software is kind of a little blurry. But okay, so for this class, here's some examples. We'll kind of just be example driven in this class about types of system software. Libraries are one. So if you've ever used printf or malloc, these are all part of C standard libraries or Unix standard libraries. Programming tool chains, so all of the programs that take your software into machine code. And programming environments like editors like Vim and Emacs, building tools like Make, and version control like Git. So these are the tools that we're more or less going to cover in this class. You'll use libraries. We won't write any libraries in this class, but we'll actually write some of these pieces of the system software. Questions on this? Arguments? Thoughts? Different thoughts? Yeah.
What is L? What is like? Is it L? What is it? What is the linker? I forgot.
Oh, we'll go over that near the end of the course. It combines multiple binary. If you compile your program, it's in machine code, and then if you have two different C files, and you want to combine them into a single program, use a linker to do that. We'll go over that a little bit. Actually, we'll go over that near the end of the course when we talk about compilers. Any disagreements with this definition or examples? Okay, so by the end of the course, and some of you actually pointed this out already, there's a few things, like 5 kind of competencies that I hope everyone will walk away with. And one is understand the file system. So too often students go through computer science without a basic understanding of hierarchical file systems. And partly is because modern OSs just kind of hide this complexity from you. You just search for things. Mac gives you the Finder. And so some of you may be looking to someone, some of you might be thinking, oh, this is easy. I'm going to ace this class. There's no problem. And others you might be thinking, yeah, I've never actually looked at the command line and found my file. I let my operating system do it for me. But the important thing to learn here is that this file system was not found in nature. It was developed by people. And the homework you're going to do tonight is you're going to read about the development of that file system. And so you have to learn it. So you can't take for granted that you just have to know it in computing. And so we're going to actually learn the hierarchical file system in this class. So some of you might find that easy. Some of you might find that perplexing. But I want to make sure everybody's on the same page and that you don't leave computer science thinking, where are my files on my machine? So again, it's like my machine does it for me. I'm at the whim of whatever my machine does. Instead, if you know this, you'll be able to understand what the operating system is doing under the hood. Yeah?
I remember, in security and computing, particularly in CS1, I had trouble finding my file directory and stuff because when I was trying to run my files and use this.
Exactly. So we will learn how to use the file system. That's one of the first things we'll do. Secondly is the command line. So just like with the file system, you've probably seen people next to you are just like ninjas on the command line. You're like, oh man, I'm doing really bad in this computer science, but it's not really taught. You're just sort of expected to know it, expected to be proficient at it. So we'll actually go into using the command line, and along the way we'll learn about the kind of system software and operating system design that you're exposed to with the command line. So if you've ever wondered why bother learn the command line, well, it exposes you to really almost the full power of your machine and the operating system. There's a lot more you can do in the command line than you can with special purpose applications. And we'll see that starting next week or in a couple weeks. There's also a lot more software, probably, that does not have a graphical interface. I haven't measured that, but I'm pretty sure it's true. And using the command line allows you to download and run just a lot more software that other people have written. You can also do massive amounts of automation. So something where you sat down and said, well, I need to write a C program or a Python program for, there may be a bunch of tools that already exist that you can glue together, kind of like Lego blocks, to make programs that are as powerful or more powerful and faster than you could just write by hand in like Python. And we're actually going to use this in this course for grading. We're going to automatically grade your programming projects, and my graders and TAs will write software that automatically grades it so that they're not downloading, building, testing 290 projects every couple of weeks. And so just to give a little illustration about how powerful the command line is, who's heard of the Linux kernel? Probably have a device that uses it. It's over 20 million lines of code and thousands of developers. And you can actually develop for that. You could contribute to it. You could get the code, build it, run it, modify it. You could send emails to the developers. You can patch it. You can submit it entirely on the command line. Yes, even email, even calendars. There are command line tools for doing this, and many Linux developers do it this way. They do things entirely on the command line. And so that's what we're going to learn in this class. We're actually going to learn how to do the entire software development lifecycle just with that maybe esoteric to some command line. Okay, so addition to the file system and the command line, one thing that goes together with the Unix command line is the Unix philosophy. And we're not going to go too deep into this, but one of the reasons that we can build up complicated tools without having to write new software is because of this Unix philosophy, this idea of having well-defined small tools, which we'll see starting next week, that you can cobble together to solve larger problems without having to actually reinvent the wheel or write code. And I put some links here if you're interested in reading more about this. It's in the notes. And similarly, in order to do all your development on the command line, the development environment I've picked is the GNU Linux, as controversially some people like to call it, but the GNU development tools like GCC, Make, which are developed by this GNU organization and used on Linux operating systems. And so I want to make sure everybody knows the kind of classic development workflow and sees how to do it on the command line. Because when you go to a job, they're probably not going to use, unless you're lucky, I think, you're probably not going to be using all command line, depending on where you go. You probably have to use an IDE. And you don't want to go into the internet and say I'm really good at Eclipse. But you're using Microsoft. Oh, yeah, I don't know that. Instead, you want to say, well, yeah, I understand the development process. I know all these low-level tools. I know how they fit together. And it'll make you able to learn really any development process because they're all largely the same. And you can put them together with these low-level tools. And lastly, I actually want everyone to get their hands dirty building some of this system software. We're going to build a very simple shell. We're going to build a command line tool, so you'll see how it actually works under the hood. We'll build other command line utilities, and we'll build a low-level compiler. You'll see how linking works. You'll actually be able to write C code and code in your language and have them call each other, have them run each other. Okay, any questions about that? Those are kind of the 5 competencies I want everyone to walk away with. Yeah?
Because we're dealing with lower level system stuff,
Yeah.
Will we run into issues if we're just emulating Linux like on WSL or VMware or something like that?
You could with WSL. That's why, so the difference in this one, I didn't put it here, but I'll show when I go to the syllabus. Everything will be on Eustace, for better or worse, so that will unify everybody's development environment. I haven't actually used Eustace for a class before. I have heard issues people have it if everyone's using it, but I think they've upgraded some of their machines, so hopefully it'll work out. Yeah.
So that's what you're just using Eustace for first time this class? Because as I remember, in the spring 24 or up till then, you didn't use Eustace.
Yeah, I required everyone to use virtualization, but there was a lot of people with machines that were older, and I felt like I was shutting out people who couldn't afford a $3,000 laptop or something. So I figured the way to equalize it is use Eustace, because everyone will have the same system. And that's from what your colleague asked, that's kind of matter when doing systems programming. There are minor differences, even in C libraries and C development tool chains. But everything will be standardized by using Eustace. All right, so I like to give a little kind of change log in the software development style from previous courses. So this course is a complete redesign from last year. I've expanded content on the actual core system software stuff, which is the namesake of this course. As one of my GTAs pointed out, it's kind of broader instead of deep into compilers. As a little ad for my class, which I teach in spring, I teach graduate compilers, which undergraduates can take. And that will kind of dovetail into this course if you want to learn more deeply into the compiler world. I love compilers, but not everyone does, and there's a bigger world of system software that I think you can all benefit from. Programming projects are a little easier because they're sort of more well-defined, but there's more of them. And I also have a very lenient late policy for projects. I've modified this a little bit to not just let anyone turn it in at any time before the end of the semester, but you have to turn in the project first, even if you completely fail it, in order to resubmit it. And the reason for that is some student, it was meant to help students organize their time, but some students were waiting sometimes till after the class was over to start their project. So I want to make sure everyone is just on time, and even if you actually made the effort of just pushing the project, even if it doesn't work at all, just submit something so that you stay aware of the class. So those are the big changes. So from the previous offering, so I have some other past change logs here. The students were asking about sort of competency questions for the class. So I've turned this into homework. And homework is not meant to be hard. It's not graded for 100% accuracy. It's effort. But every single class will have a homework. And it's meant to take an hour or less, I hope. Maybe the readings might be a little more, but they're meant to be ideally pretty fast, but they're for basically every lecture. To keep everyone on topic, make sure you're aware of what we're trying to learn. And then from the previous one, all the stuff's been incorporated already, so it's not really that relevant anymore. Okay, so my actual kind of secret motive here is to make everybody good at programming, to give you all those tools that you need to be good at programming. And it turns out that a lot of it really has little to do with the actual coding. It has a lot to do with your workflows, knowing the coding environment, knowing your tools. And so to kind of, and also there's a philosophy about developing software that I want to kind of imbue in everyone, especially when you're doing large-scale, complicated projects that you can't just hack together overnight. I know maybe many of you can just hack together a 200-line program and it works. That's much harder to do when you're dealing with, say, a 20 million line program like Linux. It will, whatever strategy you have is probably going to break down at 20 million lines. So to hopefully not infantilize you too much, I have a little allegory that I'd like to use to illustrate this software development philosophy, and it's based on what I think everyone knows, the tortoise and the hare. So these two characters, the tortoise and hare, they're both giving a challenging programming project. So what does the hare do? The hare starts coding, right? That makes sense, because the faster you finish the code, the faster you're done, right? You just got to get through it. Stay up overnight, get those 200 lines out, and you're done. What the tortoise does is the tortoise doesn't even write code. The tortoise starts writing planning documents. They start writing tests. I don't know how you write tests without code. Can you write tests without code? The tortoise does. Writes comments before even a single line of code gets written. And it may seem so slow that the hare actually just finishes coding their whole project. The problem is that after the code is done, that's when all the real hard work begins in software development. And that's because when the hare is given one of the tests from me or the GTA, the program is, of course, going to break. I don't know, has anyone ever written, say, 2,000-line program that had 0 bugs? Probably not, right? Some people may, I think, can, but 20 million lines, probably not. So it's going to break. And so what does the hare do? You got to go fast. Move fast, break things, right? They start guessing, changing code, running the test again. And okay, I got it to work. But now another test is breaking. And actually fixing that bug actually just broke another test, frustratingly. And so the hare might just be thrashing back and forth for a while. And if they're lucky, they might actually get all tests working. And some of you, I know, have done this. I've done this. So everyone's done this. But the hare's going to be surprised by a bad grade because we keep secret test cases that we don't share with you. And in all likelihood, they will break if you've developed things in this way for a substantially large program. The tortoise, instead, before they even code, they start breaking the problem down into simple pieces. So for instance, when I have to write a new program, I literally write hello world because I'm almost 90% sure I can get that right. And if I break it, it's pretty easy to debug. So the tortoise breaks things down into simple pieces, and we'll show software architecture a little bit in this class, but it's not really a software design class. You'll see that in like OOP. The tortoise writes simple examples. They write tests. Even before you have code, you can actually write tests, and you can at least write specifications of the input and output. Tortoise takes some easy piece of the problem, like hello world or reading a file. It doesn't write code. They write comments to say, okay, I got to read the file in here. Okay, how do I handle the path? Let me write a comment there. And only then does the tortoise start writing line by line, little by little, in the tortoise way. Little bit lines of code, testing as they go. Every line, testing. And the tortoise makes sure that simple things work before moving on. You don't want to be the person calling tech support and they say, did you plug it in? You want to handle all the simple stuff first, right? You want to make it easy for you rather than fast. So the tortoise doesn't take for granted that the code works, because the tortoise knows debugging is really hard, especially when you have lots and lots of bugs, as the hare discovered the hard way. So it seemed like the hare took a lot longer to get code out, and they did. They took a lot longer to actually get a line of code. But when he got there, the code was much easier to write correctly, and it probably works in most cases. So to reiterate this, while the hare was just coding, the tortoise was writing tests, writing comments. You can think of it as pseudocode, but it doesn't have to be that formal. It can be just like comments about what's supposed to happen. And carefully thinking about each line of code, testing all along the way. And so when the tortoise gets the big test cases that we have, they're probably going to pass. But they're not all going to pass. Nobody's perfect. So the ones that don't, he isolates the test case. He makes a small version of the test case, as small as possible. This is called test case minimization. And he uses that to actually isolate where the problem is in the code. And because the code is well documented, you had comments before you wrote and organized, it's much, much easier to find where in the code it's broken. And this feels a lot slower and a lot more kind of cognitively demanding because you have to kind of consider each line of code. It's a little, can be frustrating and feel slow. But overall, amortized over the time of coding, the tortoise is actually faster for, I argue, a large enough and complicated enough code base. Of course, everyone can hack together small code, but 10 million lines of code, probably not. So my ulterior motive here is be the tortoise when you're coding, especially in this class, because when we do this low-level system software, it's not easy. It's not easy like Python. No error handling is happening for you. You have pointers to deal with. It's tough coding. A 40-line piece of C code is going to be tough to get right. So one caveat here, as I said, is there are cases where you hack, for sure. I'm not saying never hack. I do all the time. I write fast test cases. You don't want to do it on like the airplane you're flying on, but on your own code, if you're just like organizing your music library or something, hack things together, hack away. Okay, thoughts on the allegory? Does that hint at something or make seem kind of clear? Okay, but that's all well and good to have this allegory. How do we actually do this? So, first thing you can do is know how your programming language works. Don't just guess what the code is going to do. I mean, sure, if you're uncertain, you can write a little test and figure it out kind of empirically. But one benefit of this class, we're going to dig into how programming languages work a little bit. And so you'll have a better understanding of how your programming language actually works. For instance, pointers. You'll understand at the machine level what a pointer is in C. So this is a key one that I see a lot in students who feel like they're struggling, is knowing the programming environment. So coding is not all about C. It's also about the environment you use. So having really fast workflows to run tests and then modify code, run tests. If you feel like you're slow, spending a lot of time typing on the command line, there's lots of tricks for making that fast. That you'll look to your neighbor and say, wow, they're really fast, but they learned it. They learned it somewhere, and I'm going to show you some of these tricks in this class. So just like the tortoise did, break the problem down before coding. Just like tools were made for man, man was not made for tools. Use the programming language tools to help you. You don't have to write a function just because functions are there and then be at the whim of whatever that program does. Use it for the right purpose, which is to break your program down into useful chunks. As you'll see in later classes, you'll learn about refactoring and other techniques. This is a critical one. Make sure simple stuff works before moving on. Don't be lazy in the way that says, well, I don't have to test this because this is just reading a file. What could go wrong? It can go wrong for sure. Trust me. I make lots of buggy code. Write your own tests. Save your tests. Don't overwrite the same file with your new test, because then you lost all that work you did making a test. And there's a technique called regression testing where you can take old tests that work, rerun them, and make sure they don't break again. Because what happened to the hare? Some of the fixes he made actually broke old tests. And part of this is a programming environment workflow issue. Like if you're not fast at, say, making new files or opening up editors or switching back and forth between your compiler and running, then you can feel like it's really slow to make new files. And we'll hopefully help solve that. And finally, develop good debugging skills. So I have a little schema here for debugging, and we'll go over it again in the class. But the schema for debugging is just like with coding. You don't start with a code, you start with a test. And you try to narrow the test down as small as possible, especially in programming languages. Narrow it down to the smallest test that will still trigger your bug. And that will make it much easier to identify where the bug is in your program. And understand why the bug happens before trying to fix. Don't hack fixes thinking, I'm guessing this is going to work. Let me just test it. It'll be slower overall. It'll work in some cases, but I argue it'll be slower overall. So this is not me inventing. This is not my wisdom. So Brian Kernighan, one of the original AT&T Unix guys, wrote this in Elements of Programming Style, something like half a century ago at this point, I think. Everyone knows debugging is twice as hard as writing a program in the first place. So if you're as clever as you can be when you write it, how will you debug it? So if you're hacking together in the most clever, fast way possible, you've given yourself a rat's nest of a debugging problem. So take your time, be the tortoise, and do things the simple, easy, slow, clear way to write code, and then debugging will be that much easier. Okay, so just to kind of drive home a couple more points. Systems programming, which we're going to do in this class, will help you become a better programmer because you're going to understand how programming languages and their environments are actually implemented, so you'll know what the tools are doing. You'll know how the programming environment works. And we have very light theory in this class, but if you've ever struggled with discrete or computational complexity and wondered, why do I have to learn this, or any math, really, theory is a tool that makes programming easier. So functions are probably easy for you now because you've used them. But that's a theoretical tool. There's no actual function implementation in the machine code level, I argue. You can argue with me if you want, but the machine does not actually know how to run a function. There's no command at Intel that says, run a function. There's a call command, but it's not actually a function. Okay, and so I just want to leave you, before we get to the syllabus, leave you with this kind of classic 3 Virtues of a Great Programmer by Larry Wall. So some of them might surprise you. Laziness is one, and it's not the laziness that the hare did. The hare actually spent more work. It's the laziness that the tortoise did, doing simple things first. Reduce energy expenditure, use automation, which is why knowing your programming environment helps. Impatience. If you feel like it's really slow to use your tool chain, find a faster way. There are faster ways. And hubris. This is a tricky one because it's the bravery to let someone else look at your code, which you may think, I don't want anyone looking at my code. But it's good to do that because you'll, just like any writing, you'll write it in a way, hopefully, that someone else will be able to look at it and understand what your code does. Okay, anyway, all the stuff is linked in the introduction. So before I move on to the syllabus, questions at all about the introduction so far? Okay, so let's go over the syllabus and the course in detail. All right, so just make sure everyone's in the right. Oh, yeah, go ahead.
Is there any way to use these outside?
I'm sorry, can you say that aloud?
Use these outside.
Oh, yeah, absolutely. You can connect through the VPN. There are instructions on the syllabus. I'll point you to them. You can absolutely contact Eustace from outside with the VPN. So I've tried to give you all the tools you need. I tried to leave as few assumptions as I can in actually completing the course. So yes, you can access Eustace from outside. All right, so just make sure everyone's in the right place. This is section 1. There was a long wait list, and the department added a lab, I think, so that everyone on the wait list, at least as of several days ago, would be able to access the course. I don't know how it works. I don't know the registration system, as I said, how you actually do the registration. But from my understanding, everyone that was on the wait list several days ago, there should be room for them now. I don't know if other people signed up for the wait list. If you have any questions, ask the department, or your academic advisor for questions. So yeah, we're in section 1. Prerequisites. I'm assuming you all have the prerequisites. I'm assuming everyone knows where we are, where we're meant to be. Here's the final. That date was already defined by the UCF calendar. There's information about instructors and TAs. We'll use a discussion board called EdSTEM for discussions in the course. If you have anything more personal or private to talk about, you can email me. But I'll be much faster to respond to course-related content on our discussion board. So labs, there's a 4th lab added. So Brent, my magnificent graduate student, will be teaching that lab. He is in the VIM camp, while I'm in the Emacs camp. We'll talk about that later. So, but he's also a very, very good programmer. He'll be covering the labs, where we'll just review the material in this course. Office hours will be manned by me and my other graduate student, Sanan. I have not made these yet. Just to take a little quick poll, I'm thinking of doing them after the class, Tuesday, Thursday at 1:30. Who cannot come to that? Okay, pretty small number, maybe. Pretty small number, okay. Of those people who can't come to that, can you come Wednesday? Can you not come Wednesday at 1:30? But you also can't come Tuesday and Thursday.
I don't know. Maybe just because like my, oh no, my gosh.
I'll send out a poll.
Oh, wait, I can't come Wednesday. Right. I can't come Wednesday. You're right.
Okay, so it seems like, so there'll be some combination of office hours where ideally almost everyone will be able to come out. I don't know if I can get every last person, but I'll send out a poll on Ed discussions as well, since there are some people who may not be able to come.
Ed discussions or?
Ed discussions, yeah.
But we haven't got, when that starts in like the second week.
Yeah, it starts in the second week, but there's no office hours this week. You can email me if you have questions. Okay, here's the schedule. So it's grouped to very much cover cover the stuff that I talked about in the introduction. So this is the introduction from today. I want to point out that I will strive to record every lecture. I can't necessarily guarantee that. This is not an online course, but I do that for convenience. So if you miss a class or I'm not taking attendance, but you should be coming to class. It's an in-person class. So this video, once up, will be linked here on YouTube. I'll have a digital whiteboard, which I have here. And if we do any stuff in class, I'll put a PDF to that here. And then every lecture's homework assignment will be given here. So I'll go over it more in the assignments, but this homework is due the following lecture. So this is the assignment date or the assignment schedule.
But you made it due Friday.
So this one is due Friday for the academic activity requirement, but all the other ones will be due the next lecture. But I made this align, the homework one align with the academic activity. So if you're on financial aid, this is the homework to do. It's supposed to follow the academic activity requirements. But all other ones will be due the following lecture. Yeah. At latest, I'll do it during the lecture or by the end of the lecture, if that seems fair.
Like every end of the lecture?
Yeah, or maybe the beginning of it. Yeah. Does that seem fair? Are you looking for like getting ahead of the homeworks? If you're interested in getting ahead of the homework, yeah, let me know. Maybe I should take a poll on that as well. Let me take some notes here. So most people can do Tuesday, Thursday office hours. Most of those can do Wednesday. Who can't? Can do Wednesday.
No, I can do Wednesday office hours, or, I don't know, I just,
Well, I'll send a poll out. I'll send a poll out for this. And homework ahead of time. So I'll put some homeworks out. I'll try to put some out, I don't know, a little more ahead of time. And you can give me feedback if it's too little or doesn't matter. Okay, sure. Okay, and then as we'll projects are not due for a little while, but this column will be the assignment date. So that's when, I guess just like homework, that's when it'll guarantee to be published to do the homework. I guess some people may want to get ahead of this as well. And so I'll, if I get feedback on this, let me know. I'll try to strive to get these out earlier, but these are going to be the latest date that you'll get the assignment. And this column is the due day, or due date, and the time will be listed below, but this is the due date. So the Hello World project, which sounds like an easy project, right? Hello World is assigned here, and then you've got like 2 weeks to turn it in here or 2 weeks of lectures. I think it's not a full 2 weeks, right? 12 days. Okay, so that's the schedule, or that's the way the schedule works. I've grouped this into the kind of areas that we're going to cover. So we're going to cover the file system in the abstract, kind of academically, next time. And then we're going to dig into using the command line. Some of this might be simple for many of you. I'll put some sort of, hopefully some more fancy stuff in here that you can try out that you haven't seen. I'm always learning stuff on the command line, new tools, new techniques. So hopefully there'll be something for everyone, even if you've done this before. And then we'll learn about the programming environment. I suspect even those who are good at the command line may have less familiarity with, say, writing make files or using Git. And so we'll learn all about that here, how they work. And we'll actually build a Hello World program. So it'll take all the difficulty of writing code out and put it all in the program environment. So you'll actually have to use a command line editor, and you'll have to record yourself using it to make sure everyone actually uses it. And there's, surprise, surprise, a command line tool for recording command line sessions called Script. And so we'll use that little trick. If you've never seen that before, you can actually record your command line sessions. And that's what you'll submit. You'll submit this complete developed project with version control, with a build system for a simple, lowly Hello World program. Then we'll learn about systems programming. So this is the real kind of building system software part. We'll learn about actually using files at the system level. Oh yeah, go ahead.
Just wondering, when you say record, does it record the screen or just record the log of your program?
It records the text and the timings. Yeah. So it's not so that's the benefit of it is it's very, very parsimonious compared to like an MP4 file or something. So it is a text-based recording system. I guess if you're really clever, you might be able to subvert us, but we're gonna if you're doing that, then you might as well just record it. Okay, so we'll actually get into systems programming. So how you actually use your operating system. I think OS, this sort of overlaps with OS, but this is more from the view of actually trying to build some system software. So we're going to build a command that will list files. It'll have some extra bells and whistles, so it's not just a pure ls or dir command. We'll learn about process creation and process I/O, and that will help us actually build a command line shell. So you'll actually build a very simple command line shell, and you'll see it's not much more than like 50 lines to build a command line processor. And so you can see how it uses the kernel and the access to kind of the virtualized hardware that the kernel gives you to run a command line processor. And that's why the shell is, I think that's why it's called a shell, because it's a very lightweight interface over your operating system. But it gives you exposure to lots of the functionality of the operating system, which we'll see here. We'll see here all the functionality of the OS that you can exploit from the command line. There will be a midterm in this class. I can't remember my rationalization. I think I just wanted to break up the class a little bit. And it's in person. It'll be in the class. It'll also mean you don't have to like remember so much for the final. I think that's why I strategically added it. Both exams will have a review session. So the lecture before it will have a review session. I'll give you the format of the tests. I'm not trying to trick you with formats or anything. You'll have a limited number of notes you can bring with you. If you need SAS, I have those emails that'll be set up for you. Yeah, so we'll have a midterm exam. All right, yeah, go ahead.
Is it paper?
It's paper. It'll be paper. Yeah, I can't think of a good way to do, digital. I know there are techniques, but invasive techniques, but yeah, I'm just going back to old school paper and pencil. Okay, so the first half is kind of using and building system software, and the second half preserves this system software history of compilers, which I love. I love the compiler world. But here we're going to focus on more the back end, the low-level parts of the compiler. In particular, we're going to see how source code actually not just gets turned into machine code or intermediate code or virtual machine code. We're going to see how it actually goes through the operating system, because the operating system is involved in invoking programs. And we'll see how some of these kind of classic programming tools work, like functions and library calls, how they actually work at the systems level. And we'll build tools that will spit out machine code that will interoperate with the rest of your system. You'll be able to use GCC and other tools to combine your software with other C software and other C libraries. So I think that's pretty cool to look at, because you actually see how this works under the hood. It is a little complicated, but it'll be a kind of simplified version of this. We're not going to deal with some of the more sophisticated techniques like dynamic loading and things like this. And then it'll be a pretty straight ahead compilers course at this point, where we're going to see how each of these language features, which I'm sure all of you have used in C, actually get implemented at the low level, particularly pointers. So pointers are, I think, always mysterious for students at the beginning. We'll actually see how these translate into, and we're going to use Intel, because we're on Eustace, we're going to use Intel machine code. We'll see how these actually translate into Intel machine code, how functions work, and hopefully that'll open your eyes a little bit to how, they're simple in a way that makes them hard to use, but they are fairly straightforward in their implementation. They're just kind of complicated to think about. And then, we'll have a final exam review. So this is Thanksgiving week, so I'm going to put a special topics class there that probably is not going to be on the exam. I don't know yet, but I'm guessing people will be out. So I put the review the week before in case people are out. And then the final exam, during the final exam period. And there'll be more details about the final exam. I have not written these yet, but they'll be based on the homework, the projects, and the lectures. And you'll have some limited amount of notes that you can bring. But I'll give you a practice exam before both of these, so you'll have some expectation about the content. Questions about schedule? It's pretty intense. We're going through a lot of topics pretty fast, but I'm trying to go a little more broad than deep. This is the first time I'm offering this, so I haven't calibrated pacing yet. You can give me feedback, on the project submission. Remember, the project submissions is a very lenient late policy, and homeworks. But yeah, you can let me know. I haven't calibrated exactly yet the pacing of the course, but I think we can get through all of this. Okay, so let me tell you about the grading structure. So this is all the kind of mechanics of the course, so it's very, very clear to you exactly how you're going to be graded. So one thing I like to do is make a point in the class on any assignment, 1 percentage point of the grade. So you don't have to play with web courses or ask me what's my grade going to be. You can very easily compute your own grade. So you just see how many points have been given so far. So if there's 10 homeworks in one project, that's like 20 points, and you've got 15, then you have an estimated grade, right? If you've got 15% or 15 out of 20. So that hopefully that makes things more straightforward. These are all the categories of things that you get grades for. So first is homework. There'll be roughly 1 per lecture, 1 for all the lectures that have content. There's 8 projects. There's a midterm and a final, and this mysterious participation category. All right, so let me go over each of these, what they are, when they're due, how they're graded. So, so homework is due before the following lecture, 11:59 a.m. I sort of like 24-hour time because it makes this less confusing, but this lecture is at noon, and before the lecture, in my definition, means 11:59 a.m. So get it in web courses. So for example, here's a lot of numbers here. Homework 15 is assigned in lecture 17 on 10:15, and it's due the following lecture 18. But let me show you the schedule, which will make it a lot easier to see that. So homework, I'm confusing myself now. So homework 15 is here. Homework 15 is assigned after this lecture. So it'll be a homework about parsing. And it'll be due the following lecture, before the following lecture. Questions on that? Does that make sense? So whatever the following lecture is, so that includes, say, the review. So whatever the following like class that we're meeting, this is going to be due. So Web Courses does have all of these deadlines already set, so you should see them in Web Courses. Questions about that? There's no late for homeworks, sadly, because I'm just going to go over the homework in the next class. It's meant for you to like keep up with the class. But they're not graded for correctness. Not 100% correctness. They're graded for like a genuine effort to do it, to read or answer the questions. So, don't freak out like, oh, I'm going to wait and try to argue for getting late because I don't want to lose points because it's like not complete. Just submit it. Submit what you have. Yeah. Oh, that's a good. Well, I guess if you get it wrong, so you'll see homework 2. Maybe I'll put homework 2 up. So homework 1 is due Friday, because it's the academic activity. Homework 2, I'll show you next time homework 2. So it's a little complicated. You have to like figure out a file system, infer a file system tree. And so if you just get it wrong, like you make a little mistake or you make a couple mistakes, you're still going to get the point. So for example, I'm going to give you, I feel like publishing it, but I'm going to give you a list of file paths, and then you have to construct the tree out of the file paths. So it's a little puzzle solving exercise. But you might get something wrong, you might forget something. You're still going to get a point if you just submit that broken result. If you just submit like a blank thing, we have graders are going to check those. So try not to subvert the yeah.
So basically when you say giving effort, basically you're trying to say like if we show our work, you basically
Yeah, that would be an example. So the homeworks are going to vary quite a bit. So some are just going to be like, so one of the homeworks is do the Emacs or Vim tutorial. And so it's very hard to check that. So I have a little question, survey questions about it. Some is like this file system exercise where it's a very concrete answer. Some are like readings and then like tell me what you learned kind of things. So there's a variety of them. And we're just, we just want to make sure people aren't, trying to subvert the grade, like actually keep up with the course. They're meant to be an hour or less. So I guess if you're taking genuinely working at it and it takes you like 3 hours, don't do that. Take an hour. The reading might be a little longer. I haven't calibrated the reading, but just do it. Genuinely try to do it. And we're going to have a little, sanity check to make sure nobody's completely like just putting blank stuff or copying yes or something. Unless I ask for it, just say yes. Some places I may ask you to do that, but just so you're not just putting the number 0 and saying, oh, I got it wrong. So. Just try to, academic code, read the rest of the syllabus, academic integrity, actually try to do it. We're going to have a little sanity check. But I don't want this to be like a big headache for you. I know anything requiring punctuality is annoying, but these are not meant to be like hurting you on your grade. These are meant to be kind of freebie points, actually. Like, unless you really messed up your schedule or you have a legitimate, like, you're out for medical reasons or something, this shouldn't be an issue, I think. It's really just planning. And I hate kind of grading people on their ability to be punctual because I was never good at that. But these are like meant to be really easy. These are meant to be easy. But you can let me know if it's like you're spending 3 hours on it. Don't do that. Let me know it's like this is hard. Or come to office hours or lab to get feedback on it. Questions on homework? So because we go over it, I don't know how to do late for that because we're just going to go over the answer next time. But the way I compensate is, it's not graded for like correctness. You're not going to get 0 if you actually tried to do it. Okay, projects. Projects are quite different. So these are due on the date in the schedule by 11:59 p.m., end of day. It's because the lecture happens to be at noon, so that's why we have this same looking number, but that's why I bolded this to make it clear that the projects are due the end of day, 11:59 p.m. So for instance, this Hello World project, you'll get it on or before September 5th in a couple of weeks. And it'll be due September 17th at the very end of the day, 11:59 p.m. Eastern time, Florida time. That make sense? Okay. Okay, so this is the change from previous years. You must make some submission by the due date, something. Put something in the repo to see that you're like, alive and you're doing the course. You haven't completely dropped out or something. If you don't do that, then you can't resubmit. But if you do that, even if it's like very, very basic, you can submit as often as you like for regrading. I mean, you have to ask the TAs to regrade, but you can resubmit and retry as much as you like. So that way you'll see the grade and you'll say, okay, I got some private cases wrong. Let me go to office hours, because I really want you to actually like finish the project and not just like be incentivized to cheat or rush through it because you're like, I got to get the grade. So I want you to actually try to like finish these projects, because I think they're fun, I think, outside of the class context. But I think they're also valuable, and they're not that big, and you'll be able to resubmit them as much as you like. So, in the kind of behavioral economics way, I'd like to make it, no penalty for late, but then like everyone's just going to turn in late. So there's a very, very, very tiny point deduction, 0.5 of a point. So you can still get an A, if you turn everything in late. And there's opportunities for bonus projects to kind of compensate for that. But this is really just kind of a behavior hacking to say like, oh, you're going to get a little penalty. So, try to turn it in with that. Yeah.
When you think per project, is it per project that you submit late?
Yeah, so there's 8 projects, and so you'll receive a maximum of 4 points deduction, eight deductions. You won't get it every time you submit it. It's a one-time penalty for resubmitting. So yeah, here's an example here. Here's a couple examples. So somebody submits this My LS project on 10/3 after the due date. That's their first submission. They receive no points, and they can't resubmit. A student submits the project on 10/1 by the due date, but they totally crash and burn. They fail it. But then they submit a fully working project 11/19, well before the final deadline, and they get 5.5 out of 6 because it works perfectly, but they get a 0.5 deduction, and they can resubmit as much as they want. And so and then the rock star student who's like hacking away all night long, they submit it on the due date and they get a perfect score, and that's the way you'll get 6 out of 6. So this is not meant to be like killing your grade. This is meant to be hack your behavior a little bit, to say like you get a little penalty for late. Yeah.
And then for the grading criteria, it's based on most recent submission?
Yeah. So we don't have like, it'd be nice if we had sort of continuous integration set up. We do have Git set up on Eustis, thanks to Steve and Dick and the IT people at CECS. They've actually set up a Git server for us and the classes. It's feasible to have continuous integration, but instead you'll like ask a GTA and say, I need you to regrade this, please regrade it. And we'll try to do it, I don't know, weekly, something like that, or try to do it on demand. I'll talk with depends on how much demand we get for it, but we'll try to get it, as quickly as possible. Or you can come to office hours and I'll try to rerun it.
You
Yeah.
have to create a GitHub account.
No more GitHub. So another big change in this class is no more GitHub, thankfully. Too many students were dragging and dropping to the website, giving themselves merge conflicts. And this way, Git is entirely on the command line. You have to use the command line, more or less. There are ways around it, of course. But
That's going to be hard.
We'll learn how to submit it. So right here, we're going to go over version control. That's why we have a Hello World program. So a program that I know everyone will be able to write correctly, including myself. But you'll learn here how to use Git, actually. And so you'll know if you've successfully done it. And I have code or commands that'll show you how to actually check yourself. So that's the beauty of this kind of DIY, open source world, test everything yourself, is you can actually just grade yourself, except for our private test cases. But in the real world, you're not going to have some, authority on high who knows all the test cases. You're going to have to develop it yourself. But I'll show you how you can actually check yourself that you've submitted it properly and that it's working properly. We'll show you basically the commands we run to grade it, and you can just run those yourself. Probably we should share the automation script too, but we haven't developed them yet. I haven't figured it out. But I'll give you the commands you can run to actually check that you've submitted your project via Git properly. So you won't, So you can always it's like, I say this to my students, it's kind of like, you're in a forest, you don't have a map. It's kind of make your own map. If you just run through the forest in circles, you're going to get dehydrated and maybe die. But if you make a little map and record your steps along the way, then it'll look like you know what you're doing. It'll look like you know what you're doing, but really you're just using these cognitive tools to not rely just on your own kind of iffy memory and iffy abilities. So that's what these tools, that's the tools made for man, man not for tools. So these tools will help you verify yourself that your code is working, if that makes sense. We'll see when we get there. I'm seeing some puzzled looks, but we'll see when we get there. All right, other questions? Other questions on projects? Yeah.
Are they group projects or are they like solo?
No, they're all individual. Did I put this here? I didn't put this here. They're all individual. Let me make a note to clarify that. Actually, maybe. I don't remember if I say that, but yeah, they're all individual projects. No group projects. I tried that once, but I won't do that again. Yeah, no group projects. Not for this class. Not for this class. You'll do group projects in like when you actually do software development, where you actually need separation of labor. But this class, everyone should be competent at the projects. Yeah.
Though they're individual, are we allowed to like ask for the code?
Oh yeah, this is hard. I've seen other syllabi in other schools where they really clearly articulate this. I'm just going to kind of defer to the, what do they call it, the golden rule? Or the golden rule? I'm going to defer to that about academic dishonesty. So there's text here that describes unauthorized assistance. Just, do it yourself. But, a lot of the material is going to be like documented online. Like, how do I read a file in Unix? There's like billions of examples. ChatGPT can write it. I probably can't write the examples we're going to give, I don't think. GTA is actually testing that out. But I think the examples, they might get you part of the way there, but then you'll have trouble with the exams. That's why I did the exams in person, because if you don't know how the system works, then you're not going to pass the exam. But this is like common enough tools that there's like voluminous open documentation about using this stuff in examples. So yeah, I'm going to just defer to the policy statements here about unauthorized assistance. So use your best judgment. Yeah, don't share like code. I mean, some of the documentation just has code in it. Like, here's how you open a process. The book will have it. And so you can use that. That's not unauthorized assistance because they're giving you the book. But it's putting it together that is the real challenge, the kind of Lego building and the puzzle solving that is the challenge. And if in doubt, ask me. Or come to office hours with your friend or something, and, maybe I can supervise or something. But use your best judgment in this. Don't cheat, basically. All right. Other questions on projects? So it'll hopefully become clear when we get there. Okay, so midterm and final. Yeah, go ahead.
I'm confused. I said there's no GitHub.
Aha, there's no GitHub. Git is not GitHub, and GitHub is not Git. So yeah, GitHub is one of the more popular centralizers of a decentralized version control system. But Git is a decentralized tool that anyone can install. You can install it on your own machine and be the official. And there's no one official.
How do I install Git though?
It's on Eustace already. It's already there.
I don't know how to do that. It's doing so hard.
It's not gonna be hard. I'm gonna walk you through every single command that you need to run. Just practice. It'll be like muscle memory. You gotta practice a little bit. Okay, midterm and final. It's got to be taken from homework, projects, and lectures. So projects, so that you're not just like blatantly cheating and not understanding what the code does. So I'll ask you stuff, about writing code. Maybe there's certainly electronic ways to cheat on paper tests, but they're, I think, a little bit harder. But yeah, if you know the stuff from the class and you can kind of at least know the concepts of the system programming, if not the specific details, you should be fine on the final. But there will be questions from the projects as well. We'll do an in-class review, as I said. There'll be very limited open notes. The in-class review will have like a version of the test with different questions, but a similar format. So you don't get. I'm not measuring format, like leakage of format understanding, which is a real thing in testing. Okay, participation. This is the fluffy one. So I don't really have any specific thing to do for participation, but some examples of participation is showing up to class. But attendance is not taken, but if you show up to class and sort of can match the face of the name, asking or answering questions during class, participating in class discussions on EdSTEM, our discussion board, coming to office hours, just be present, be physically here if you are physically able to, and always, of course, let me know if there are sort of administrative or medical or other issues that are preventing this kind of participation. But that's very small. It's like 4 points. So now all the numbers are nice, binary style numbers. So that's why the participation kind of works out that way.
Are you taking attendance? Or?
No, I'm not taking attendance. and something I also have done in the past, which is very, very hard to think of that. You can do it through quizzes, actually. That's one way to do it. All right, so bonus projects. So this is even more fluffy and more vague. I'll kind of pepper projects with like bonus things to try. So I kind of give it's kind of like a video game, like a Nintendo style video game where it's like there's like an easy way through it, and then there's more challenges in there. So I'll sprinkle some extra challenges for you to try, the kind of harder versions of the shell, or extra things you can do with LS, or more complicated things you can do with the programming language. But really, this is on you. This is not formalized, so propose it to me or come to office hours at some point before the final exam, before all the projects are due. Up to 6 points because it'll recoup. Actually, it recoups more than the bonus, more than the. It's 8 projects, yeah. So it'll recoup a little more than what you would lose from late projects. So it's one way to kind of compensate the late penalty. Questions on that? I know these are more vague. It'll be more clear as the class goes on if you want to. And if you have an idea yourself, they just, hey, I want to implement. So I had students that I want to implement arrays in this language, which we don't have. And they're like, okay, yeah, try that. That sounds good. And they did it. Questions on this? Okay, so this is a letter grade scheme that I've used for many years. I haven't had an issue with it. Anybody have an issue with letter grade scheme? I sort of reserve the right to use a minus, but I don't know if I ever have. Maybe, but this is the scheme. I think I just took it from a prior instructor. Okay, so I think this is the last part. So let me go over logistics. So this is a guide that will show you everything you need to complete this course. All the tools, where to find them, guides on using things. So for the syllabus, I know there's a syllabus on WebCourse as well. I'm going to keep the syllabus here as kind of the up-to-date one for everyone. Lecture notes, so every time I have a class, I'm going to publish the slides in a lecture notes format, the videos, homework assignments, the actual descriptions of the homework assignments, project descriptions. These will all be available on this website, which is linked from WebCourses. So basically everything, all the kind of textual content you need to complete the course will be here on the website. So for projects, let me go to homework first actually. So homeworks, to make it a little confusing, is on WebCourses. So there are kind of, if you've seen WebCourses like homework 1 through 24, and you'll have to do a little matching exercise to make sure you put the right homework in the right spot, because I just opened them all up. That's on WebCourses. So that's the only thing you need WebCourses for is submitting homeworks and just the links to the syllabus and the discussion board. That's all you'll need WebCourses for.
What about your grade?
Your grade is also, yes, your grade is also there. So your official grade will be there. But I mean, for the interaction that you guys have to accessing the course and contributing to the course, that's all you need WebCourses for. So yeah, we will use that. That is the official system we use. It'll go to your grade eventually. So that's all WebCourses is for. Project submission and implementation will be on Eustace for the implementation. So everyone should have access to Eustace now. And we're going to test on Eustace as well. So if you want to go use a virtual machine or test on your own machine, it's kind of at your own risk. You can certainly come to us and say, hey, I want to regrade it. You can also, it's Git, so you can also just clone it back to Eustace and try it there. You can test it out there. So feel free to develop on the command line if you really want to go that route, but I expect project implementation to be Eustace. So that's the service that UCF is providing for the project implementation. Project submission will be via the Git server, and I'll talk about that in a second. We'll actually do that through Eustace on the command line entirely to submit the code to Git. And so if you've never done this before, which many of you I think haven't, you probably wouldn't have had to do this, not for class usually. We'll have a very careful set of instructions on how to actually do this, and then hopefully you'll get good at it and you'll learn. I've had a lot of students say, I'm really glad I learned Git. I went to an internship and they were using Git and it was no problem for me. Even if you use the Git UI, Git has very kind of some esoteric parts to it. So even if you have a UI, it's not going to help you understand what Git is doing. But if you use the command line, very fine-grained, it'll show you exactly each step of using version control on the command line, at least Git version control. Okay, and then for all questions and discussions, aside from, you can send private messages on ed discussions. Me and the TAs will be more likely to answer questions there. or faster. My inbox is very large, but if you have like personal or other kind of procedural issues, you can of course send me an email, and send me an email again or come to office hours and we can discuss. But I expect that all questions and discussions, announcements will be on Ed Discussion. Has anyone used Ed Discussion before? Who's used it? Oh, okay, very, very few. Okay. Okay, so that's the overview of the logistics. So computing resources, because I don't want to assume you even have a laptop or a computer or even one that like works really effectively. UCF actually provides loaner equipment, right? Do I have this right? I think they do. They actually provide loaner equipment. And there's computer labs that I think you can go access Eustace and complete the programming assignments with. And you can actually borrow laptops, which I found out. So you can actually do this course without, very minimal cost besides like tuition or if you're on a scholarship. Very little equipment cost. Here's web courses. I assume everyone kind of knows this already, so I just linked to their support. So if you haven't used it, let me know if you have questions, but you can check out the support online. Okay, so here's the Eustace instructions. So this is the server. You put your NID, your password. Who's not used Eustace? Oh, okay, so in some number. Yeah, I don't know how prevalent it is for like CS1, CS2. Maybe some people use it.
It's just in CIS.
Oh, just in CIS.
Yeah, it's not used in any other class.
Oh, yeah. People used to use it, and actually, there's a guide here from a prior offering of the course. Yeah.
Montang or Levins?
Well, Jim Lansky, when he was here, had a guide here. What were you gonna say?
I think it depends on the semester, but my classroom have used it for CS1 and CS2.
Okay.
I think it's mostly Stanford. I know my professor for CS1 didn't use it. He just kind of like created his own thing.
Okay, so it's kind of professor dependent. So it seems like a lot of you did. I'm kind of reviving it using Eustace again. I think they've upgraded hardware. I don't know in Eustace, but at some point over the years, and they've added other servers like the Git server, the machine that the Git server is running on. So this is how you'll connect. Now you're probably wondering, well, how do I do that? Where do I type that in? We'll go over that in class. I'm not going to go over all systems. I'm going to put guides here for each operating system how to run this command. So if you're on Linux, it's very easy. You just open the terminal. If you're on Mac, it's very easy. You open the terminal application, and you can run this command, replacing your NID. And if you're within the campus firewall, you'll be able to access Eustace. If you're outside of campus, you can use the VPN. So I put a link here to the instructions. They might be out of date. I put it to the search results because they recently, I think they changed how the connection works at some point over the past years. But so I've put a link to tech support on that. And also some guides here from other professors, Zumlansky and I think this is Kevin Moran. And if you really want to get fancy and not have to type your password every time, you can check out this guide on setting up an SSH key. But okay, so this is the Git server, and we will go over how to use Git. We'll go how to actually make repositories on this. So great thanks to Stephen Dick and CCS who set up the Git server, and we worked out how to configure it and everything. And so you'll just be able to create repositories under your name at will for all the projects. Okay, and this is EdStem. So I'll just send you guys an invitation on EdStem through your NIDs. Okay, 5 minutes left, and we're almost done the syllabus. I know there's a lot of content. I just want to make sure everyone is clear on all the mechanics. So these are required textbooks that are free for you to access. So also special thanks to Lily Dubach at the University Libraries who got this book for us. This is a really nice, more modern C book, and the first 5 chapters are not about C code, but about programming environment, which is perfect for this class. So we'll learn about make and auto tools and stuff. Now there are some pretty wonky instructions for actually getting this material, which I will go through briefly now, for both of these actually. Look over these instructions very carefully. There's a little illustration here. The one thing to not do is read online. If you read online, your institution has one copy, you will block other students and make them very unhappy, and then we'll have to go to the library and get them to unlock it. Do not read online. The thing to do is to download chapters, and you can download PDFs. They're not DRM'd or anything. You can download up to a certain amount per day. I know it's very wonky, licensing, but this is how we got free textbooks for you guys. And so these set of chapters for this book can all be downloaded in a single day by a student. So you can download all these in one day. If you mess up or download a different chapter, you just wait till the next day. I know it's a little wonky, but follow these instructions and it will give you access to digital free copies. Do not pirate them, but digital copies of this textbook. And same for this book. Okay, and questions? Yeah. Curve? No curve. I don't believe in curving, at least not now. So my goal is to have a kind of well-defined absolute set of competencies and abilities you should have, and you should meet those. And I try to make them reasonable for all people taking this course. So no curve. It also means cheating doesn't hurt your colleagues. Yeah. We know assignments for the lab. There's no lab this week, and lab will just be review of the material. So Brett will prepare some material, and then you'll be able to ask questions. Yeah. That I don't know. I guess if there's space, but I would ask the department if that. Yeah. It will be the same teacher though. All right, everyone. Have a good one. See you Thursday. Homework is up.